Problem statement says a feed that is 1,000 moles per hour of, of 50% acetone and 50% methanol must be separated into nearly pure components. Assume that the equilibrium data is well approximated by the Margulies model. Design a system using multiple flash tanks and each operating at 1.5 atmosphere absolute pressure. Then try to achieve the separation with a single distillation column. And part B is something else. But we are going to try the multiple flash tank approach, something that we tried way back in January for the first time. Remember when I got multiple flash tanks all in series, I'm sending my initial mixture and then splitting it. And I keep splitting it until at the very end, I want to get, probably got too many flash tanks here, but just the idea is that I want to get 90% pure of component 1 and 90% pure component 2 in the top. 90% pure. All right, so let's first acclimate ourselves to the diagram. Remember, the idea here is that we want to set, I have a degree of freedom here. So I said set temperature or the fraction of the feed vaporized. So I have to choose either one or the other to set. I think just for sake of illustration here, it doesn't really matter. I think it's a little bit easier. What if I just said that V over F was going to be equal to 1/2 every time? So we take the feed, we chop it into 2 equal parts. So I'm going to say 1,000 moles per hour and split it into 500 moles per hour in both product streams. And then it's a flash tank. So just keep doing it again. 250 moles per hour to all of these. And now the idea is to figure out what temperature I need all these flash tanks that are going in series to run. So 250, 250, 125, 125, 125. I don't even know if I'm going to need some more flash tanks. I probably will, maybe not. Let's go ahead and see. It's a design type problem, so I have to design, well, I guess it's more of an evaluate type problem. Well, it's kind of both because I have the ability to keep adding stages if I want to, but I can specify the temperature that I want as well. All right, 1,000 moles, 50-50. So I am starting somewhere here. So I've got a liquid mixture. It doesn't tell me what temperature it is. I'm going to assume it's a liquid. I could easily have assumed it's a vapor and the problem will work out the same way. But I have to set a temperature here. And if I want a 50-50 split, then that means I have to have a temperature such that my vapor and liquid would be approximately 50-50. Graphically, what that looks like on the TXY is I have a point that's right in the middle of my 2 lines. So I'd say it's something like so. All right, and I would read the compositions off the graph. So I've got 58%, 45%. And I'm going to say component A is acetone, make it easy on myself, A for acetone. So in the vapor phase, I've got 58% acetone and 45% acetone down here. And also to make things easy, I'm only going to specify what my acetone mole fraction is. I'm not going to worry about what my methanol mole fraction is because I always know that it's 100% minus acetone mole fraction. All right, so I've got, let's do the liquid side first. If I split that in half again, then I'm going to be splitting along this line. So I want to pick a temperature at which I split my moles equally. So I have to pick a temperature where my point is right in the middle. So it does not too far up. Be a little bit warmer. And that gets me an even split. I also forgot to say what temperature this is. Let's say 62.5, it looks like. 62.5 degrees C. Down here at the bottom, I've got 63 even, it looks like, maybe a hair above 63. All right, I've got 54% acetone in the top And I've got 38% acetone in the bottom. Oh, and by the way, I've been doing this with the TXY diagram. You could do this with the XY diagram as well. You just have to you have to do one more step to figure out what the temperature is. So remember what the operating line is for a flash tank. So it's, you could look up what the equation is. I actually have to go back and look it up myself. This is my flash tank operating line. I've specified already that V over F is equal to 1/2, and therefore L is equal to V. So my slope is going to be YA is negative 1 XA plus 2 ZA. So going back based on whatever ZA is, remember I start from Z because my operating line is going to intersect the Y equals X line at Z. These are all concepts that I'm very deliberately calling back from earlier in the term. You should be remembering all these things, and if not, it's not a big problem. Just go back and check your notes. So there is an operating line of slope -1, and I can use this point now to read what the points are. So here again, I've got 58% in the vapor phase, and 40, what did I say it was? Supposed to be 45, right? Did I mess this up? So I think the issue here is just merely my precision. If I zoom in, I should have been doing it with this level of precision probably the whole time. But this line's probably a little bit more crooked than it should be. Also, I guess another problem with doing it with the TXY diagram is that I have to guess where the halfway point is. So I want to make it so that my green point is halfway in between the bubble point and the dew point curves. That's a little bit harder to do. So probably this is somewhere between 40 and 45. And then over here, I've got an intersection that also happens somewhere between 40 and 45. So I'd encourage you to do a little bit more precision when you're doing problems like this by hand. But it's not going to affect the point that I want to make. And maybe some of you already see where this is going. But if I try to keep doing this, the idea is I can keep adding stages to the bottom, and it's not a problem really. I can keep taking the liquid. So the liquid is where the the bubble point line meets the tie line, and then keep drawing more and more stages, and I will get more and more pure. So what I'm doing here is I'm taking my liquid again, and that becomes my new Z, my new feed composition to my next stage. I'm heating it up until my point is equidistant between the dark blue curve and the light blue curve. And if I keep doing that, eventually I'm going to get down to 10%. So in one more stage, it looks like maybe something like that. I've got it down to less than 10%. So I'd say that the bottoms can easily get to 90% pure methanol. Right, but over on my top, I've got a problem. And that problem is that if I try to do the same thing, but for the tops where I've got 58% acetone, and now I try to do the same thing, but now I'm going to have to go the other way. So I'm going to have to cool it down a little bit to get to equilibrium. And now when I cool it down here, now I'm going closer and closer to the azeotrope. So I'm going to have to keep zooming in. But the idea is that the azeotrope represents kind of a roadblock to distillation. In other words, I can't pass the azeotrope ever because the bubble point and the dew point curves come together. So there's no way to go to the other side. Remember, if I want to get to 90% pure acetone, at some point, I have to get a tie line that's like so. So you might say, well, I need to have 63 degrees C in my flash tank, but I've already had a flash tank that operates at 63 C, and my product compositions were not 90% acetone. So I can't get to the other side of the azeotrope, and that's an issue. Let's see what happens if we try to do it in a distillation column. So I'm going to pause and erase. So let's instead try to solve this problem with a single distillation column. So it's typically how we don't usually do a bunch of flash tanks in series. We'll specify it with a total condenser and a partial reboiler, as we've done. This reminds me of happier times actually teaching in person, drawing all these diagrams up on the board. 1,000 moles per hour, 50-50, 50% acetone, 50% methanol. And I don't know what my flow rate is, but I know that acetone is my, quote, more volatile. Or it doesn't really make sense to say more volatile when you have an azeotrope. But anyway, these are what my specifications of the problem are. Now, if I try to design the problem how I typically do, so reflux ratio is a degree of freedom that I have. But remember that my my RSOL is y is equal to r over r plus 1 x plus xd over r plus 1. Right? I think that's it. So similar, remember how we used to plot the lines? I intersect the y equals x line at xd, and my slope is r over r plus 1. I'm going through these a little bit quickly. Remember to go through your notes and double check that this stuff makes sense. So at xd, which is 90%, so I start my RSOL here, and already I'm confused, right? So no reflux ratio will give me a line that makes any sense. So unless I can't cross the equilibrium diagram, so I'm going to have to stage step. It doesn't even make sense to stage step from the bottom. So I'm going to have to start from the bottom somehow. Or you know what? I don't even think it's worth trying to explain how you would go about approaching this. The issue is that I have to have an XD that is on one side of the azeotrope and an XB that is on the other side of the azeotrope. And I can't do that by stage stepping because this represents kind of a pinch point here. If I ever have stages that are in here, they're going to be way too close and way too intricate. I'm going to need infinite stages just to get there, and then even when I do get there, I can't get past it. So I'm going to leave that at that today. Next time we're going to talk about a clever way called pressure swing distillation to get around this problem using two distillation columns with different pressures. And then I'm going to leave this second part of the problem to you as well. So if it were 80% acetone and 20% methanol, I'll just give you a hint that the essence of the problem doesn't change at all. It just makes it so that I can get pure acetone but not pure methanol. So it switches the problem. I can get pure of one component but not pure of the other component. All right, that's all for today.